the square of your amperage times the resistance on it. The resistance is in ohms, the amperage is in amperage because we're in America. And so the reason why this is important, it's easiest to show with gear ratio. If you know me, then you know that my mantra is volt up, gear down, or in some cases, kV up, gear down if you can't go into a higher voltage. The reason why I talk about that is easiest to explain in a little formula. Let's say that you go from 11 tooth pinion to a 10 tooth pinion. That's a 10% difference in your gear ratio. So 1.1 would be the representation of your ratio change, and this is in a good way, a gear down way for us crawlers. The amperage is going to be a direct ratio to your gear down. So if you gear down by 10%, you're going to have 10% more amperage for any given load. We multiply the amperage by itself. Let's just assume, let's convert this ratio into an amperage. So at an 11 tooth pinion, you have, let's do it this way, 11 tooth pinion, we have 1.1 amps. And on a 10 tooth pinion, we just have 10% there, 10% difference in gearing, 10% difference in our amperage. So we multiply the 1.1 times itself.
If you're missing out, John Holmes of Holmes Hobbies is doing motor test class right now. Holmes Hobbies doing the motorcycle.
1.1 times 1.1 is 1.21. So I'll just make the conclusion for you. If you go down in ratio by 10%, you get 21% less heat in your system. This is both in your ESC, technically your battery, but batteries don't run hot in crawlers, and also in your motor. So if you can imagine 21% more heat if we went from a 10 tooth pinion to an 11 tooth pinion in the other direction. Just a few teeth in a pinion change can make a huge difference in heat. It quickly turns into something you can't stay in front of, honestly. And it's the same problem you would have if you're racing, if you're drag racing, any sort of RC realm. But with a crawler, we don't have such a large motor that we can kind of map the heat through the actual thermal capacity of the motor. In a drag racer, you're going down there, you've done in 3 seconds. The motor's not going to heat up, at least on that first pull, until you pull it off and you wait 45 seconds or it's going to start to heat so through those coils into the outside. You can't do that on a crawler course because you're going to be out there, well, having fun like this, you're going to be out there for hours at a time. So it doesn't have the benefit of just that heat ability of the motor to mask what your gearing may be if your gearing is wrong. So this is really the basis for the entire volt up, gear down. KV up, gear down really doesn't work the same because you're asking for more and more with a higher KV. But this is why gearing is actually important. A 20% change would be, let's see, I'll just do it on my calculator here. 20% change, 1.2 times 1.2. 1.44. Yeah, so if you go up 2 teeth from a 10 tooth pinion to a 12 tooth pinion, that's 44% more heat in your motor, in your ESC, and technically in the battery, but the batteries in a crawler usually don't have a hard time. So this is why it's very important to have it geared properly, not to have it over-geared, and also at the same time to use a motor that's at your typical speed for crawling. And that gets into my next points that are going to be talking about racing motors versus crawling motors. Unless if somebody has questions on this in particular, maybe the nuts and bolts of it or anything like that. Yeah, question? Did I see? I don't know, just a wave. Right, so the difference between race motors and crawler motors really boils down to a race motor. Not only do a lot of times you have rules that say you can only have this much, you can only have a stator with this ID or a rotor of this diameter. They also have limits in most of the classes on the copper fill. The more copper you have into a motor, the better it's going to do for torque. But in a racing situation, well, you don't necessarily need more torque, but you need RPM, you need power at the end of the track. So that's kind of where they go with them. They go for RPM. Race motors are almost always RPM based. They do everything in the book to make them faster. And if y'all follow any of the racing and the gray area that they've been doing lately, they'll have a lamination stack and they'll put some air in it, or maybe they don't get the lamination stack all the way compressed on there. Or maybe they short it, do it by 3 laminations on one side, or maybe they put tapered laminations on the end. That is all for RPM, nothing but RPM. But if you get an RPM motor and you bog it down in the rocks, it starts to create that heat. And since it's a race motor, for any given KV, you're going to have a much higher resistance for it. So it's going to create even more heat. Now, I'm not saying that race motors won't work in a crawler. That's not the case. You want to make sure that it's going to be something slow by 2700 kV, but what race motor is actually rated in kV these days? They're all turn counts. It doesn't work out. But to give you an idea about my two poles versus the racing two pole, are 13.5, let me make sure I'm doing this right, our 10.5 turn motor, 3300 kV. The average 3300 kV you get off the shelf is like a 17.5 turn motor. If you're looking to produce torque, that's not the right way to go. Again, you'll probably be fine in the crawler. If you got a race motor, throw it in the crawler, see if it works. It probably will. 13.5 and 17.5, whatever, it's probably going to be fine. But if you want something that's actually optimized for a crawler, surprise, buy a crawler motor. So really all it boils down to. But all the tricks that they use in racing do a really big disservice to crawlers. They don't tune them for low speed control. They don't tune them to have good torque density. They want them to have an RPM density, if you will. So it just really doesn't work out long term. It's not optimized. You can save some weight by going to a crawler motor versus a race motor. You can have better torque density, you can have better low speed control, better throttle modulation, and even better efficiency under that load, under the torque load. Because the torque is generated by amps, and as you can see, as the amps go up by the square, your heat goes up really fast. So, long story short, there is a difference between crawler motors and race motors. Yeah, it is for a lot of people. And some companies might just be rebranding some race motors out there for crawling. I'm not going to name any names at all, but it's not me because I got nothing to do with racing, so I can't do that. All right, I think that covers it unless anybody's got any specific questions about race motors, crawler motors.
I had a question sort of on going back to the gearing.
Yeah.
How does, when you overdrive, say, the front axle, how does that affect what you were talking about in regards to gearing?
So when you're overdriving the front axle, you are in essence increasing your gear ratio, but it's not fully by the overdrive amount because you'll have that difference. Essentially, you'll have a scrubbing average speed gear reduction change. So let's say we went up by 10% in the front. On average, you're going to see about 5% more load on there. Plus, depending on your traction, you're scrubbing in between your front and your rear axle. Now, on the positive side of that, all of our motors are kind of designed to have good torque density. At least crawlers are definitely designed for torque density, and you don't have to worry about it overloading your motor too much. And when you go to a smaller motor, and if you go to a ridiculous amount of overdrive, some guys run at 50% overdrive, it can actually make a really high load. Your runtime will go down. You will notice that. And if you run an overdrive versus just a straight 0% overdrive, you'll probably notice at least a little bit of runtime difference, if not a lot, and then also more heat on your motor. The entire system just runs a little bit warmer. But if you're out here on the trails with sand and everything, it's not that big of a deal. Now, if you get into the rocks, if you're constantly crawling on the rocks, it becomes more noticeable. But of course, you don't need as much, at least in my opinion, of OD when you have a high grip surface versus a low grip surface. And that's something that everybody has to tune for themselves. Your tires, your foams, your driving style, how much up or down you have on courses. I think I did that backwards, down or up on courses.
Yep.
It's one of those things that there is no right answer. I tend to like about 30% overdrive on my comp rig.
I'm 30 to 35% on my comp rig.
Yeah, and that seems to work for most people, but it does make things run warmer. And if it's a really small motor, something like a Puller 400, you notice a difference. At the end of the run, it will warm up more, just because your final ratio is technically a little taller because of that front pull, that front thing that you have. I call it dig all the time, and people are like, what are you talking about? Oh, overdrive. Back in the day, we called it front dig because it would kind of dig you around. Yeah, and if you think about the ultimate front dig, it's when you have the rear locked and your ratio is infinitely more on the front than it would be on the rear at that point. So it's just as a habit, I call it front dig, front ratio, whatever you want to call it. So, yeah. So it does affect just the same formulas. It's just a little weird because your front and your rear are spinning at different speeds, so a little bit harder to calculate.
Okay.
Yeah. Any other generic questions before I move on to my non-list here? Because I didn't put a whole lot of stuff down for today. Because last time I did, I feel like I may have done one of these numbers. Any specific questions? I'll just start talking about motor theory. Y'all are cool with that. I keep looking at this cutout back here. He has a question. Oh, he's really like it. He's really involved in this.
He did have his hand up earlier.
Yeah.
First time I walked by, cut out and called my attention.
Yeah. We have a cutout of Snoop Dogg in the shop. And every time I walk through, I see Snoop stand there. Whoa, somebody's in my shop overnight.
We had one of Shaquille O'Neal, and we were house sitting friends of ours, stuck it in his front window. When he came home, he walked up. He's like, "Who's in the house?"
Yeah. Right.
Scared.
The next topic that I'll talk about, if y'all want to hear about it, is the beaten torque of the motor. The beaten torque is how hard the shaft is to turn. There's other ways to describe it. Cogging torque is one term that's used. And you can actually represent this in grams, would be one function. And essentially you put an arm on the shaft of your motor and you spin your motor housing, and how much force it takes to make the motor shaft turn is your beaten torque or your cogging torque force. This is going to be a trade-off on torque density versus low speed control on pretty much any topology across the board. This is always going to be our trade-off. Just like I have the Crawl Master version and I have the Torque Master version of the motor, that is essentially me tweaking the beaten torque or the cogging force of the motor to make it either smoother starting or have more torque density. When you have more torque density, you always have more drag density. You'll almost always have more efficiency under high load, but you will trade off that low speed control, that really low speed finesse. Now this is talking about brush motors in general. Brushless is getting to the point to where we can kind of ignore that and do the magic of 32-bit software, FOC or micro-stepping, there's a lot of different ways. We can, I'll have to talk about that next time, I think, because there's not a lot for me to say right now. But for brushed motors at least, it's always that trade-off of low speed control versus the torque density. And this goes for any motor, any brushless motor off the shelf. If I tweak the magnetics of it to go one way to have a smoother startup, it's not going to have as much torque density. But in a crawler, we have enough torque density usually, especially in brushless. Anything 4-pole and up, even 2-pole, honestly, plenty of torque. And so for me, at least, as a crawler, I want that really smooth startup. And that's why we have the Crawl Master version or the Torque Master version. Or in our 8-Skill Flow Pros, we have the smooth version and we have the punchy version, just so that I can give people that choice. I would say in the revolvers, I've tweaked the magnetics over the years. At first I was going to more and more torque density, then I went softer and softer startup, a little bit less torque density. Now I'm actually working back towards the other direction because, like I said a few minutes ago, with the Magic brushless, we can actually force poorer starting up motors to start up better than they normally would these days, which is kind of cool. And this is more or less a new development. FOC in other realms have had this for a really long time. In e-bikes, we've had FOC for over a decade. Field-oriented control, torque vectoring is another way to put that. I'll just throw all the terms at you. You don't have to remember them. But that is something that we've used in the e-bike realm for a long time to get a motor that you can't even turn the shaft by hand. No way, no how. And we're talking about rotors that are this big, motors yay big, 15 to 30 pound motors. Can't turn it by hand, but with FOC, it knows the position of the rotor and it can kind of tickle it through. If anybody is a CNC machinist, you know what micro-stepping is. And essentially we're doing the same thing as micro-stepping, but instead of saying, I won't get into the hard switching of that, but more or less, it's micro-stepping it and finessing it through what would normally be those hard deep positions of it's here, thunk, it's in the next position, thunk, it's in the next position. We can really smoothly do that at this point with brushless. The average controller from Castle can't do it right now. Y'all have seen from Hobby Wing, the Axe uses FOC to kind of smoothly step it through, although they also made the rotor have a very low deaton torque, kind of a disservice to the rotor long term in my opinion. But they were able to do that with that. Also the Fusion is using that topology as well.
I have 2 of those.
And so you can tell it's really smooth starting on the low end. They did end up doing some things for optimizing on the low speed control versus torque density on that. I won't get into that because that's talking about other companies' engineering. I don't want to get too much there. But that's a trade-off that we're actually going to see less and less of in the future, that we can get more torque dense motors and still retain that smooth startup that I would normally have to say, I need to reduce this deaton torque, I need to reduce this cogging force so that it's smooth on the low end. With brushless, the years are numbered of having to do that, which is really cool. I've been redesigning the revolvers just for that, for our Crawl Master ESC. It essentially micro-steps the motor through, and you can watch it start up. It spins so slow. It's pretty amazing. Even to me, I've been doing it a couple years behind the scenes. It's still really amazing to see and to know that in the future, in 2 more years, that we may not have motors that aren't smooth starting at all in the crawler scene, which is really cool to think about. Have all the torque that you want, all the hold brake that you want, without having to burn amperage to have a hold brake like the Fusion and the Axe. Because it is such a smooth rolling motor, they actually have to burn amperage. They have to inject heat into the motor to get it to hold, the hill hold, or whatever they call it in the programming. The programming can do that. But if I can take a motor and increase that deaton torque up to the point where you can't even spin it by hand, then you no longer need to burn that lubricant. You can just sit on a hill, it's not going to go anywhere, and then we can more or less micro step it to get a smooth startup and essentially have no compromises in between the ESC and the motor. I know this was talking about motors, we're supposed to be talking about motors here, but with brushless at least, the controllers are almost more of the performance of this part than what the motors are, at least now. 2 years ago, I wouldn't be saying that. I didn't talk about it at all last time I did this because it wasn't on the table really. But now, I'm excited for the future. Really excited. Yeah, beating force and slow speed. There you go, in a nutshell. That's what that is. Any other questions pertaining to that, or where baby's coming from? Any last questions? See, when mommy and daddy love a stork a lot, they adopt a stork. Stork flies in. Yeah, the stork flies in and it steals a few $100s a week extra. Mommy and daddy are happy. That's just very cheap.
Right.
Are there different ESCs or everything is PWM?
That's a great question. So his question is, are there different ESCs or is everything PWM? At the root level, all ESCs have to use PWM. They can't only use commutational cycles. So a normal motor, a Castle ESC, a Tekin ESC, one of my normal ESCs, it all uses 6-step commutation. So you have 3 wires on that ESC, and you can kind of envision, how many different ways can we connect 2 wires. We're going to step here, that's 1, we're going to step here, that's 2, we're going to step here, that's 3, we're going to step here, that's 4. Well, I went through 3, then we reverse, 5, 6, I suppose it would be, but there's 6 steps to turn a motor. I think I did that right. 1, a 2, a 3, a 4, a 5, a 6. There we go. 6-step commutation for a 2-pole motor. There we go. 2-pole motor, that is 1 revolution. For a 4-pole motor, that is a half revolution. Revolution for an 8-pole motor, it will be a quarter of a revolution, etc., etc. So you can actually multiply it by the 6 steps to know how many commutation cycles for 1 rotation of your motor. That's why high pole count motors start up smoother in a crawler. We have more commutation cycles per revolution to get there. I'm not answering your question at all right now. So we've got our commutation cycle, our 6-step commutation cycle for a normal 6-step controller. This would be our universal controller, a Tekin, a Castle, a Holmes, a Hobby, a normal controller, etc. Now on top of that commutation, we also have to have PWM so that we can control, so we can regulate the speed. And the commutation rate also has to match what the PWM rate tells the motor to do. And then the kV of the motor is giving us essentially a feedback, a back EMF, saying, am I going fast enough or am I not going fast enough? Increase the PWM or decrease the PWM with commutation frequency, or, and the other way to do it would be to adjust the commutation frequency to match the PWM that the motor's trying to spin at. It's kind of complicated. But they all use it. And we go to the Hobby wings that they have now, the Axe and the Fusion, it still has to use PWM to control what's going into the motor. Because if you have a 3-cell LiPo and it just gave it 100% all the time, it would just burn up, honestly. Or it wouldn't easily keep sync as the commutation frequency is trying to rise and keep up with what the PWM is telling it to do. But all ESCs have to use PWM in some way or another, unless you have some sort of synchronous AC waveform on the backside that you could use that instead. But then we're talking about 3-phase industrial motors, and that doesn't really pertain to a crawler, I suppose. So I won't talk about that. But yeah, we have to use PWM. So yes, they all have to use PWM.
Got a dumb question. What is PWM?
PWM stands for pulse width modulation. Another term for it is duty cycle. If you've ever used a welder before, any welders here, the duty cycle is usually what they call it, but PWM is the exact same. So 50% duty cycle is the same as 50% PWM, and if you imagine the pulse width modulation, hey, I can actually draw something here. We would have the off state, we would have our on state up here, and with digital electronics, it's not a smooth waveform that we're switching, it's only on and off. You can't half switch a MOSFET. Although there is a little bit of what's called a slew to it. It doesn't quite turn on fast because you have to charge the gates up, but then it's on. Once you turn it on, and then it's off, and there's a little bit of a slew rate to that. So there's what we call dead time in the switching. And so if it's 50% duty cycle or 50% pulse width modulation, PWM, you're going to have essentially half on, half off at 50%. At full throttle, it's just essentially always on, and then our commutation cycle is the only thing that's controlling it at that point.
Is it possible to use a quad ESC to control a revolver?
Yes, you can use a quad ESC.
I was trying, I was failing.
So you have to use certain firmware for it.
Side-by-side hill climb,
that's what I'm
sponsored by
using on
Axial,
some of my
starts at
ESCs right now, although my branch is
2:45.
separate from the
Last
public
call to buy
AM32s.
in.
The downside of the quad
Fastest
ESCs is
time,
that they're made
walk
for higher
away with
voltage.
brand new
6S or
wrist.
8S, right?
Yeah.
When you're tuned for 6S or 8S, I almost have to draw this to really make sense. You can't have good low speed control. So with AM32, there's forcing commutation with micro stepping, and then you have to essentially wait for the back EMF of the motor to be high enough to get past your resistive bridge. If we watch the back EMF on the motor, you have to have a resistive bridge on there to do it. But if it's tuned for 6S LiPo input, you're not going to be able to see a really slow motor. So right now on a standard, let's say an high-fly ESC, we can't see a motor spinning slower than about 350 to 400 RPM. We just can't. And that, I mean, that's pretty slow to tell you the truth. But if you have an ESC like my Chromemaster ESC, it's still using a branch of AM32, which is technically like a quadcopter, but our resistive bridges are tuned for that much lower voltage. It's tuned for low speed control, so it just works a little better.
I was going to say, the only reason I was experimenting with the quad ESC is I cannot buy it.
Yes, and I wish you could. We should have the next batch in about 6 to 8 weeks, but the ICs, as y'all know, the world has been kind of upside down the last couple of years, and our lead time on ICs, as using STM Micro on that Trawlmaster, went from 20 weeks to 62 weeks in between my first and my second order. And so, you know, I thought for sure, well, I ordered enough to get to my next batch, right? And of course I didn't, because I quadrupled the lead time or tripled the lead time on me. So, yeah, I wish I had some too. It would be nice as somebody who has to sell products to live to have products to sell. That would be good. Yeah, it would be. Now, talking about quad ESCs, the BL Heli does not have...
That's what I was trying, the
Yeah,
PLL.
BL Heli does not have good startup for low speed control. It's made only for that. But if you use the AM32 branch, which is actually when BL Heli flows down to closed source, he took all of those resources that were still open source and he did his own 32-bit
Even the BL Heli 32
AM32.
won't be able to do it.
No, it does not have the same features on there. It's really not tuned. Pete, the guy that curates AM32 with me, he's a crawler. He doesn't do anything except for crawl, which it turns out is actually good if you're trying to develop crawler products. That you're a crawler, right?
Instead of trying to verify our quadcopters.
Right, but there's a lot of targets. Now, it's a hassle to do this. You're going to have to jam a bootloader on there first, and then you're going to have to find your public target as well for the ESC that you selected. I don't know how to do that, to tell you the truth. I can take the hex file and jam it on mine that already has the bootloader on there, but I have my pick and place assembler put the bootloader on there for me so that I don't have